The last section of the climbing performance is time to height. We want to know how much time it takes to the required height during the climbing. In the earlier section, we've derived the vertical speed or climb rate is a function of height, airspeed, thrust, and weight. And then the time required for an aircraft to climb from one altitude to the another can be calculated. And so we have the equation dt equals dh divided by vc. That's incremental height, and that's a climb. Vc is a climb speed, vertical speed, and dt is incremental time to achieve the height change in delta h. Okay, so the total time used from h1 to h2, we just do the integration from h1 to h2. Now we need to calculate the time used to climb. So on the graph here, we can see the horizontal axis is a vertical speed, and then vertical axis is the height. And we can see from with increasing height, the vertical speed actually decreases. So let's focus at the climb section between h1 and h2. The time used, and we call it dt, can be calculated as dh divided by vc. That's the vertical speed. Okay. So the total time used from section h1 to h2, we can do the calculation. That's t12, and the integration is from h1 until h2. Okay, so now let's play some tricks on this integration. We can, on the right hand side, we added dvc divided by dvc. That's basically 1. Okay, so now let's further assume the slope or the variation in altitude within segment 1 to 2 is constant. So that's h1 minus h2 minus h1 divided by vc2 minus vc1. So that's a slope. We consider the slope is constant, and in that case, so we can move dh by dvc out, and then in the integration we have dvc divided by vc, and that we can have dh over dvc out because we assumed it's a constant. Okay, so we do the further arrangement, just plug in the dh divided by dvc with h2 minus h1 divided by vc2 minus vc1. So this is for section 1 to 2. Okay, so if we have the summation or add all the small linear sections together, we have the total time used to climb. So here is some consideration. In practice, aircraft climb is made at a constant indicated airspeed, IAS, for ease of monitoring. This means the aircraft is actually increasing its true airspeed as it climbs. And therefore, this procedure does not constitute a steady climb, because when we do the climbing, usually the pilot makes the constant indicated airspeed or equivalent airspeed. But we know the difference between indicated airspeed and true airspeed. So that means it's with altitude increases and then the density decreases, that gives us to the increasing true airspeed. And this procedure does not constitute a steady climb then, and therefore any analysis should retain the forward speed acceleration. So in practice, we need to consider the acceleration, especially for flight analysis. A climb at constant Mach number will actually produce a fall in true airspeed, and since Mach number is involved, it's usually with supersonic or very high speed travel with increased altitude, and hence the aircraft would be trading its kinetic energy for potential energy to enable it to climb. And here's some further consideration. In practice, the aircraft control would request level off at certain altitude before a resumption of climb. And that's basically for some air traffic control purpose. I'm just not reading through. You can have a look and some additional analysis considerations during climb. Okay, here's a summary of the climbing performance. First of all, is the angle of a climb, and it's important immediately after takeoff to avoid obstacles and to minimize noise. The rate of climb is important afterwards to reach the optimum cruise altitude as quickly as possible. And secondly is the airspeed for best angle of a climb, Vx, is achieved when excess thrust is greatest. And for jet aircraft, this is very close to the minimum drag speed. The airspeed for best rate of climb, Vy, is obtained when excess power is the greatest. And also the force, Vx increases with altitude while Vy decreases with altitude. And both Vx and Vy will converge with the increasing altitude. And the converge point corresponds to the absolute ceiling altitude. And above that, the aircraft won't be able to climb. In practice, climbing is done at a constant indicated airspeed. However, the aircraft true airspeed will increase as it climbs. So in the analysis, we need to consider the acceleration turn. So it's no longer a steady climb.